That's not good. Can you maybe where's that place from? No. Too easy. Oh, can you not mute it anymore? Yes. Okay, I mean, it's kind of annoying. I don't have anything on here. Host. Okay. Yep. Sorry. Yeah, I think that's good. Okay, just double checking. Can everyone hear us on Zoom? If someone could just type in chat if you can hear us, that would be good. Yep, cool. Okay, I guess I'll just deal with it. Okay, yep. Yeah, welcome everyone. This is the 2134 finals crash course. My name is Shai and I'll be hosting the crash course. For the majority of these questions, I've just gone with questions that ELSOC has emailed me that they thought would be relevant for me to cover. So most of it's going to be like week 10 and week 9 stuff. I have chosen a couple of questions from my own final, which I'd like to go through since I don't think many people have access to that final. So let's start with a Laplace transform question, right? So this is from 2021 T1, it would have been, I think. So the question is, find the Laplace transform of the periodic function h of t in figure 7, right? So okay, so you know that the Laplace transform is defined by, so it's the integral from 0 to infinity of f of t e to the minus st dt. Okay, but here we have something that is periodic, but we don't really have a way to describe it in like a single function, right? It's a parabolic function that repeats every increments of 2, right? So for here, we're going to use a little trick called the periodicity property, but I'm going to go through how to actually derive it because I think it wouldn't be fair if I just spat some property out and then just told you to take my word for it. So let's begin by just focusing on the integral between 0 and 2, right? So I will write, so we'll write, let's consider, like, let's say g of t equals t squared for 0 between 2. Okay, so let's just focus on getting the Laplace transform of that. So yeah, okay, so it'll be between 0 and 2 of t squared e to the minus st dt. Now this integral is a bit annoying because you're going to have to do integration by parts twice, right? Because of t squared. So I'm just gonna do that. It should be pretty quick. So my u is t squared, my u dash is 2t, my v dash is e to the minus st, my v is minus e to the minus st over s. Okay. Okay. Yeah, so that gives me Yeah, that should be right. So, cool. Yeah. So I have some constant and another integral. And a constant I can just evaluate to be, so 2 squared is 4, e to the minus 2s over s, and then minus 0 because 0 squared is 0. And I've got plus this integral, so 2 on s t e to the minus st dt. And I can just do the parts integration again one last time. So let my u be 2t on s, and then u dash is just 2 on s, and my v dash is e to the minus st. My v is negative e to the minus st over s again. Great, yeah. So moving forward, I have 4e to the minus 2s over s plus and I would have inside the square brackets, so 2t on s squared e to the minus st, and there should be a minus in front of that, and then minus, and then the integral between 2 and 0 of minus 2 on s e to the minus st over s, so squared. Cool, yeah. So I'll go ahead and evaluate this. So 4e to the minus 2s on s plus, so we would have be a negative sign. Yeah. Oh, hang on. There should be a negative sign here as well because of this v. So negative. Yeah. So that gives me 4 on s squared e to the minus st. Sorry, e to the minus 2s. Cool, and then minus 0 again, or plus 0. And then we've got the integral between 0 and 2 of this exponential, which I can just write as, so 2 on s squared e to the minus st over minus s. And that is evaluated between 0 and 2. Cool. Yeah, so it's a pretty long integral, but so should just be negative, and then plus 2 on s cubed, and then e to the 0 is just 1. So we end up with this integral, which is kind of messy. I can combine it into one single fraction, which I think I'll do that now. So common denominator will be s cubed. Yeah, so minus 4 e to the minus 2s, and then s squared minus 4s e to the minus 2s minus 2 e to the minus 2s, and then plus 2 at the end. Okay, so let me just recap. We've just evaluated the integral between 0 of 2 of t squared e to the minus st, right, which is the Laplace transform of just this function, right? So how do we go from here to the function that's in the question, right? So, okay, let's do this. So let's just say that g of t, right, is just the section between 0 and 2, and this function repeats every interval of 2, right? So h of t we can write as like g of t plus g of t minus 2 plus g of t minus 3, minus 4 plus g of t minus 6, and it just basically keeps on going until infinity, right? So we've got an infinite summation of this function. Now, if you recall from the Laplace transform table, there should be a very well-known property that if you have a time delay, so f of t minus alpha, the Laplace transform of that is capital F of t, and then you've got an e to the minus a e to the minus as. Yeah. Cool. So all a time shift does in the Laplace domain is just add a phase, an exponential e to the minus alpha s. So that being said, we can write capital H of s as, so we've got, so we've got g of s, capital G of s, plus capital G of s e to the minus 2s since alpha is 2, and same thing here, e to the minus 4s, and it keeps on going. So we've got an infinite sum again, of course. And we calculated G of s, right? G of s is this. So we've got minus 4s squared e to the minus 2s, minus 4s e to the minus 2s, minus 2 e to the minus 2s plus 2. So that's G of s. And then if I just factor out G of s, I have 1 plus e to the minus 2s plus e to the minus 4s plus e to the minus 6s. And it just keeps going. So it's an infinite sum of exponentials. So those of you who did maths recently might recall that when you have an infinite sum like this, and the ratio is e to the minus 2s, right? The ratio between the one term and the next term is e to the minus 2s every time. So when you have an infinite sum like this, as long as the ratio is, actually, I don't think you call it alpha, I think you call it r or something. So as long as the ratio is, the modulus of the ratio is less than 1, then you can make the infinite, you can use this infinite sum formula, right? Which says that s of infinity is, so it's alpha, where alpha is the first term, over 1 minus r. In this case, alpha is 1, right? Because the first term is just 1. So it'd be 1 on 1 minus, and our r is e to the minus 2s. And we can use this formula as long as the modulus of e to the minus 2s is less than 1. Which, in an exam, I don't think you have to talk about this. This is just kind of for your own curiosity. But the real part of, because S is a complex number, right? It's sigma plus j omega. As long as the real part is greater than 0, then we're all good, because then we have e to the minus 2 sigma times e to the minus 2 j omega. So this thing oscillates because it's just a phasor. And this thing always has a modulus less than 1, provided that sigma is greater than 0, right? Because then you have e to the negative something, which is always less than 1. Cool, yeah. So my final answer is h of s is that fat function, which is negative 4 s squared e to the minus 2s, negative 4 s e to the minus 2s, negative 2 e to the minus 2s, plus 2. And then on the bottom, we should have 1 minus e to the minus 2s, because of the infinite sum. Yeah, and you can find this property on the Laplace table that the textbook gives you. I've just gone ahead and kind of proved why it looks like that. So does anyone have any questions with with regards to what I just did? This is 2021 term 1. On the if you're following along with the question bank on Teams, it's I think it's one of the last questions. I'm not going in order for this question, so yeah, you should be able to find it on there. Otherwise, I'll provide solutions after this Zoom call is over. All right, yeah. Okay, I think it's worth it to go through a power factor question, because I feel like Julian always puts those types of questions in his finals. So I think this question is also from my final. I'm not too sure where I got it from, but it's, oh no, I don't actually have it. Okay, no, okay, let's do a 2-point network question, because that's also, he always puts a 2-point network questions in his finals. Okay, so in a 2-point network, given the impedance parameters, so they give you the matrix itself, and they give you the frequency at which the circuit runs at. Find the Thevenin equivalent circuit at terminal AB. So this question is kind of interesting, because it's not just your standard 2-point network question. in a sense that, they have you just calculating, oh, okay, this is Z11, Z12, etc., etc. So the question is asking for the Thevenin equivalent at the terminal AB, which you can use the impedance parameters to get to. So we need the impedance seen at terminal AB, and we also need the open circuit VAB, right? When AB is open circuited, because that's the Thevenin voltage, right? So we need two things. Okay. So we have that Z22 is, so the Z22 is defined as V2 on I2 when AB is open circuited, right? I1 is 0, where this is I1. Yeah, which is 4 ohms, I think, from the matrix. Yeah, 4 ohms. And in addition to that, we have Z21 is V2 on I1 when I2 equals 0. Oh, sorry. Is that I2 equals? No, it's I1. Oh, it doesn't matter. They're both 6J. Okay. Okay, let me see. Right, yeah, we essentially have to get okay. Just give me a sec. Just trying to think about how I solved this question when I did it. Sorry, I think so this is I2, this is I1. Yeah. Okay, yeah, and this is, let's call this V2 instead of VAB, because that's what you guys are used to. So V1 on the left and V2 on the right. Yeah, so Z21 is V2 on I1 when AB is open circuited, right? So I2 is 0. Z22 is the impedance that it sees from these terminals, which is 4 ohms. Yeah. So the reason I do these two is, so the second one, the second equation here allows me to get an expression V2 equals 6J I1. Yeah. Yeah, so it allows me to get an expression for V2 here, which is, it's VAB, it's the same thing. I've just called it V2 because that's what you guys are used to with 2-port networks. So, and we're under the condition that I2 is 0, right? Which, because we're interested in the Thevenin voltage, which is when this is open circuit, right? Yeah, so we got V2 equals 6J I1, and yeah, and then we got the impedance that it sees, which is 4 ohms. And using that, we can actually calculate the Thevenin equivalent circuit, because if we just need I1, because V2 depends on I1. So how do we find I1? Well, we can use another parameter of the 2-port network, which I think is Z11, which is V1 on I1 when I2 equals 0, which is 10 ohms from the matrix. Yeah, and we have V1, right, which is, it's just 15 with a phase of 0. So that allows us to get I1 equals 15 over 10, which is 1.5. Yep. So then V2 is 6J times 1.5. And then 6J times 1.5 is 9J. So now we have now we can draw the Thevenin equivalent circuit where the voltage that it sees at terminals A, B is the open circuit voltage, which is 9J. And then it sees a resistance of 4 ohms. And then the Thevenin load is, oh, sorry, not the Thevenin load, but the actual load is 2 Henry inductor. So just recapping what I did. So we were interested in obtaining the Thevenin equivalent circuit, okay? And to do that, just from quad 1 knowledge, you have to find the Thevenin voltage, which is the voltage AB when the terminals are open circuited. And we need the input resistance that it sees. The input resistance is very easy to find, right? Because you can just look at the Z parameters, because the Z parameters, Z11 and Z22 will tell you what impedance is seen at which terminal. So Z11 tells you the impedance looking into this terminal, and Z22 tells you the impedance looking into this terminal, which is what we're interested in. So that's the reason why there's a 4 ohm resistor there. So that's the Thevenin resistance that it sees. The real trick with this question is calculating the Thevenin voltage, which I just did using analysis of the 2-port parameters. So 9J, I think, or you can also put that as 9 sine, what was the frequency? 2, okay. 9 sine 2t. And there's a 4 ohm. Yeah. Cool. So part 2, oh, sorry, not B2. So part 2 says, obtain V0t, V0 of t. Oh, okay, so VAB. So you can do that if you have the Thevenin circuit, because it's the same thing, but just as a model as a voltage source and a resistance. So V0t. So V0 is, and you can just use a voltage divider. The 2 Henry is J omega L, so 2 times J, so 4J. And V0 is 9J, so 9J times 4J over 4 plus 4J. And putting that into a calculator should give you about 6.36 with a phase of 135 degrees, or in time domain form, it's 2t plus 135 degrees volts. Okay. So the last part of this question says, determine the average power delivered to the inductor connected to the terminals A, B. And this is a bit of a trick question because, well, those of you that remember the first lab, there's no average power delivered to components like inductors or capacitors. You can go through the maths yourself. Like you could find the average power, which is the real part of, I would use the complex power, right? So it's the real part of V times I star or I conjugate, and you can work through the maths because you've got VO, and you can find the current by just doing Ohm's law in this circuit, and you'll find that the real part is 0, and that makes sense because they only have imaginary power, right? Q. So 0 watts. Okay. Yeah. Yeah. Is that fine with everyone? Does anyone have any questions? Okay. Yeah. Okay, let's do some transient analysis questions. So this is from 2018 semester 1. It's a relatively simple question, but I did have a look at it, and I don't think it's worded very nicely, which I think may be a reason why people are having trouble with this question. So I'll read the question. So for the circuit shown in figure 5, if the capacitor is charged to a voltage of 10 volts before the switch is closed at T0, then so it gets you to show the differential equation is this, state the type of response, and then find the actual I of t. Now my gripe with this question is it doesn't actually say what the polarity of that 10 volts is. I think there might be another question in a different past paper where it actually defines it as this. I simmed it in LT Spice, and it turns out that the question assumes that the polarity is like this, which is not very intuitive, and it doesn't actually say. So there's no assuming either is probably fine. So I'll do it I'll do it the way the question assumes it, which is that the capacitor is charged to 10 volts, and then this is the polarity of that 10 volts when it is hooked up to the rest of the circuit. Okay. So first of all, show that the differential equation relating the currents in the circuit is d squared I on dt squared plus 60 dr dt plus I over 7.5 microbes. Yeah, okay. So for this, we want to consider that the portion of time where t is greater than 0. So when the switch is closed, so you just have this circuit. So you've got a resistor, and then that's in series with an inductor. Okay. So here I'll probably just do nodal. So if I have the currents, if I sum up the currents, they should equal 0 from KCL. So IC plus I'll call it IL because they're the same thing, but yeah. So and IC is C dV dt. Yep. And the voltage, the other equation we can use is the voltage across the inductor is L times di on dt. And this di here is, well, it's negative IC because I'll label this IL and IC. Yep. Okay, so what can I do? Once current, what I can do is I can do I think I can find the voltage here, and I can do so V equals 90 times IL plus the voltage across the inductor, which is L. I think I'll stick to, because I think it says, yeah, okay, it's taking I's going clockwise, so I'll stick to IL here because that's what they're calling IFT. So L DIL on dt, and that's the voltage at the top node. And then I think what I can do is I can differentiate it. So dVc, so dV on dt equals 90 DIL on dt plus L d squared IL on dt. Yeah, I think that works. I mean, I can differentiate both sides. That's a legal operation. And then on the left hand, since I have dV on dt, where V is the voltage across the inductor, which is IC on C, right? So IC over C from this equation. And then I guess just by convention, IC is negative IL. So sorry, that is supposed to be a C. But if we're sticking to IL, then I'll just write negative IL. Equals 90 DIL on dt plus L d squared IL on dt squared. Sorry, d squared t. Okay, so now we have the now we should be able to rearrange and basically get the form that that the question wants us to put it in. So so that gives us L times D squared. I'll just write I because it's the same thing. I keep on writing the two in the wrong spot. Di squared on D squared T plus.
That was in the right.
D squared I on dt squared. Oh yeah, okay. Yeah. Sorry. No, so what I did is I just found an expression for the voltage at the top node just by it's the voltage across the resistor plus the voltage across the inductor. And that total voltage is the same as the voltage across the capacitance. So you can call it V or VC, I guess. But yeah, that's what I did. So yeah, sorry, my maths notation skills are pretty atrocious. So 90 times di on dt. And then we have plus IL divided by C equals 0. So all that's left to do is divide by constant L. So d t squared plus, so it should be 90 on L. And then IL divided by LC equals 0. Now I just have to sub in the constants. So just get out a calculator. So 90 divided by L is, I think L is 1.5. Yeah, so 60. So d squared I on dt squared plus 60 di on dt plus, so 1 on LC is 1.5 times C is 5 microfarads. So, oh, and I think I kept it as in the denominator. Okay. So it's, yeah, I get 7.5 times 10 to the minus 6. Cool. Yeah, sweet. Which is what the question wanted. So the next part is state the type of response, I think. Yep. So in 2134, they kind of systematically teach you to look at the equation, then calculate your alpha and omega n and just compare, and that's the type of response you have. So alpha is half of 60, which is 30, and omega n is the square root of it's the square root of the last constant. So 1 over root 7.5 times 10 to the minus 6, which is about 365 radians per second. Okay. So since alpha is less than omega n here, then we have an underdamped solution. So underdamped, which means that our I think it's called a damped frequency, right? Omega d is a square root of 365 squared minus 30 squared. So which is about 363.7 or 0.8. Yeah. Well, it depends on the response. Like if it's overdamped, then it's alpha squared minus omega, because alpha is bigger. It doesn't matter. Just take the difference, and that's your omega d. So the last part of this question is, all right, so actually solve the, okay, so since we have an underdamped solution, we know that the natural response looks something like this. Yeah, so we've got e to the minus 8 alpha t, and then we've got two constants. We've got a cosine and a sine. Yep, and then we've got the forced response, which we're going to guess is k. So if we guess k, then if we sub k into the original equation. So sub I equals K, where K is just a constant. So any derivative of a constant is 0. So you've got 0 plus 60 times 0 plus K equals 0. So K is 0. So we just have the natural response. And I mean, this should make sense because when you have no other excitation to the system, right, you just plug in a charge capacitor. Eventually it'll all decay, and then you're just left with the capacitor being open circuit and the inductor being short circuit, and there's got to be no energy in the system, right? Or the resistor is going to dissipate all of that energy. Of course, in an actual system, even if you had just an LC, it will still dissipate all that energy just due to resistive losses in the wire. But cool. So if I go back, so we're concerned in finding the constants A and B. We already have alpha and we have omega D. So all that's left is just to find A and B. So here's where our initial conditions come into play. Okay. Yeah, so this question assumed that the voltage was, yeah, like this. So V0 is, yeah, so VC0 is negative 10. So V0 is negative 10. And then what else? The current in the inductor is 0. Yeah, those are the two things that you can assume. And okay, and I'll talk about that later. Cool. So let's just sub in I of 0 equals 0. That's the simplest equation that we can start with, since I just plug in 0 and then we get this equation here. So e to the minus a of 0 is just 1. And then we've got a times cos of 0 and b times 0, since sine of 0 is just 0. So it's really neat because we can just get a constant a, which is 0. So 0 equals a. Yeah, and then so all that's left is to find the constant b. So finding a constant b is a little bit trickier. Yeah, so we're gonna use this other initial condition that we have, which is that the voltage across the capacitor before the switch is closed is negative 10. And then if we kind of pay attention to what the circuit looks like before the switch is closed, it looks like this. Or as the switch is closed, right? You connect this capacitor where the voltage here is 10 volts, and since the inductor looks like a short circuit, the voltage across and then there's no current flowing in the resistor since I of 0 is 0. So the voltage across the inductor is also negative 10. Right, because it sees this terminal and then it sees this other terminal effectively, since there's no current flowing in the resistor. So, we can say VL of 0 is negative 10. And the voltage across the inductor, remember, we can relate back to L di dt. So 1.5 times di on dt, or like I dash 0. Yeah, so now it's a matter of getting I dash of 0, which is a bit annoying because you have to differentiate this kind of exponential with two sinusoids. So I'll just do that here. So I dash of t is, so if I just use product rule, right, I can just differentiate the exponential first. So minus alpha e to the minus alpha t, and then like that. Plus, and then if I differentiate the inside, which is just differentiating two sinusoids, so I have minus omega d a cos omega d t, sorry, not cos sine. So sine and plus b omega d, and this is a cos. Cool. Yeah. So subbing in I dash of 0, so we can, so all the exponentials go to 1 and all the signs go to 0. So we have minus alpha times a, which is 0 since we found that a is 0 from the previous part. So this is 0. And then we've got b times omega d. Yep. Yeah, so from this equation, we've got that I dash of 0 is VL0 divided by 1.5. So minus 10 divided by 1.5. So our B is minus 10 over 1.5 times about 363, I think it was. Minus 10 over 1.5 times 363, which is about negative 0.018. 36 ... Right. So we essentially have both of our constants. One of them is 0, and the other one is some number. So just to recap, we found A by just making the condition that looking at the condition that the current in the inductive is 0 at the beginning, because you assume that the circuit has been at steady state for a long time. So the switch is open, which means that no current flows. So then we just sub that in and we got that A is 0. And the second condition we got from looking at the voltage across the capacitor, which consequently happened to be also the voltage across the inductor, since no current flows in a resistor. Because you make the initial conditions by looking at the voltages across capacitors and the currents across inductors. So that's what I've done here. And then I've used that to get an expression for I dash of 0, which I've plugged in t equals 0 and solved, which I get b equals that. So my final answer is I of t equals, so e to the minus alpha t, and alpha is 30. So it's a very fast decay time. And then we've got b times sine, because a is 0 and I is 0. So we're just left with b sine omega dt. So our b time, so negative 0.0184 sine 363.8, I think it was, t. And there's a ut tacked onto all of it. Yeah, so that should be the solution. I did sim it in LT Spice both ways. You get different answers, obviously, if you assume different polarities. Yeah, cool. Does anyone have any questions about that question? Okay, assuming no one has any queries, I'll just move on. Okay, so we've got another Fourier transform question. So determine a signal ft whose Fourier transform f of omega is shown in figure 8. So we've got a nice, we've got like the sum of two rectangular rect functions, I think it's called, rect t. So we've got a sum of two rectangles. So there's a couple of ways to do this question. One of those ways relies on, but I mean, both methods work. One of them is a bit quicker, because if you look at the Fourier transform table, it should have what the transform of a rect function actually is. I'll go through both ways just because I think it's more helpful to show both ways so that you can understand it a bit better. Okay, yeah, so I'll show the naive way first. Don't have any space, but sorry. Oh, I can like add a new page. Okay, easy, thanks. Yeah, okay. So I'll just sketch it again here. So, okay. Okay. And it wants the okay, it wants the inverse Fourier transform because it's asking for f of t, and we have f of omega. So it wants the inverse Fourier transform. So the inverse Fourier transform we can get by just doing a kind of naive integration of all three parts, right? We have a part that's defined as 10 between -2 and 1, and then we have another part which is defined as just constant 20 for between -1 and 1, and then we've got another one which is 10 at between 1 and 2. So I'll go through the kind of naive integration, which still works. It's just a bit lengthy. So f of t is 1 on 2 pi, and then you've got -2, -1. So the function is just constant 10, and then e to the j omega t d omega. Then I've got 1 on 2 pi times the integral between -1 and 1 of 20, e to the j omega t d omega, plus the integral between 1 and 2 of 1 and 2 pi times 10 times e to the j omega t d omega. So you can go ahead and integrate these. It's not too difficult because you're just integrating exponentials. So I just put a 1 on 2 pi out the front of the entire thing, and then I've got so 10 e to the j omega t, and since we're integrating with respect to omega, we just have a jt on the bottom. So that's between -1, -2. And then I'll go ahead and write the rest of it out. It's the same integration because it's the only thing that differs is just a constant. So and then we've got 10 e to the j omega t over jt. Okay. All that's left for us here is to just evaluate it. And remember, we're doing inverse Fourier transform, so our variable here is omega, right? We integrated with respect to omega, so we substitute the values into omega. Sometimes you get students that substitute it into t, and then that's wrong. As a sanity check, your final answer should only have t as the variable, right? Because you're going from the frequency domain to the time domain. So okay, so we've got 10 e to the j to the jt over jt. And we're subbing -1, so minus, and then we've got plus jt. I don't know. It should be minus. Yeah. So 10 e to the 2jt. Yeah. Yeah, I don't need the minus there. So I'm used to like when there's a t. Sorry, when there's an omega there. Anyways. And then here it would just be 20 e to the j omega over jt minus 20 e to the j omega. So e to the negative j omega. And there should be a negative t on jt. And then last one is yeah, sorry, these should be t's. Okay. If that hasn't lost anybody, yeah, all I've done is just the integration. Yeah, and I've subbed in all the values into omega. So I've just left with all t's. Awesome. Just got to make sure I did that right. Yep. Yeah, okay, looks good to me. So 1 on 2 pi. So now what we're going to do is we're going to kind of judiciously combine some of the terms in this expression to just, because if you remember, if by observation, right, you can see that we've got e to the jt and e to the minus jt terms, and we've got e to the 2jt and e to the minus 2jt terms. So that already kind of clues you in that we're going to get some sort of sinusoid. And well, spoiler alert, the answer is a sync function, which I'll show momentarily. So I think I'm going to collect like terms first. So I have 20 and minus 10 here. So this is just 10 e to the jt divided by jt. And then I've got 10 e to the minus jt, and then minus 20 e to the minus jt. So I can collect those as well. So we've got minus 10 e to the minus jt on jt. And then I think the only thing I have left is 10 e to the negative, positive 2jt divided by jt minus 10 e to the negative 2jt on jt. Cool. So we have 4 terms, and we're going to kind of group each of these together, because if you recall from like math 1A or 1B, when you add 2 exponentials that are complex conjugates, you just get the sinusoid. Well, when you subtract them, you should get 2 times the sine of t. So like e to the jt can be expressed as cos t plus j sine t. And then when you subtract e to the minus jt, so you get subtract cos of minus t minus j sine minus t. And cos of minus t is just cos t. So I'll just rewrite that as cos t. So these two terms actually disappear. And then sine of minus t is just negative sine of t. So I'll go ahead and fix that as well. All right, so you end up getting 2 times j times sine of t. So bearing that in mind, I can write, this is 1 on 2 pi times, so we're going to have 10, and then we're going to multiply by 2 because there's a factor of 2 out here. And then there's also a factor of j, so it actually cancels out with a j in the denominator, and we're just left with t in the denominator, and we get sine of t. And then likewise, likewise here, I've got 20 each, so 20 on t sine 2t. Just checking the solution. I might have done something wrong. 20. Uh, 20 jt. No, it should be times, because I'm subtracting them. I think there should be a 40. Just trying to see where I went wrong. 20. 10 minus 10. 20 minus 20. That checks out. No, actually, I think that checks out. Yeah. 2t. Okay, no, that checks out. Okay. Yeah. So 1 on 2 pi, and so 20 on t, sync t plus 20 on t. Sorry. Yeah, no, that's sync t. And so the sync function, recall, is it's just sine x over x. So this would be and sorry, yeah, there shouldn't be a t on the bottom, so it should just be like that. Oh, okay, yeah, so this should be 40. Yeah, this should be 40 sync to t. Oh, yeah, I've done this right. So The reason there's a 40 is because well, the x in question here is 2t. So if I just kind of write 2t on the bottom, this would have to be 40. So 40 sinc 2t, and that should be the final answer. If I just, yeah, and I'm going to divide by 2 pi, so I just have 1 on pi times 10 sinc t plus 20 sinc 2t. Yeah, so that is how you get to the answer using the naive way. By naive, I mean like there's a way to do it where you recognize that you just look at the Fourier transform table and you can go through that way, and it's a lot shorter. But you can still, this is just meant to show that you can still get to the same answer by just first principles. It might just take a little longer. Yeah, so that's the final answer. It's 2 sinc functions. And so the other way is, let me just define what the rect function actually is. So rect x is defined as a rectangle. It's just defined as a constant value between the interval minus a half and a half. So it looks like this. So it's defined as 1 in that interval and 0 everywhere else. So, and then I think if you look at the Fourier transform table that I looked at, which is, I don't know if it's, they might differ between like textbook to textbook, but the one that I looked at is rect. So that the transform pair is, if you have rect of omega over 2 times some width w, that inverse transforms to w on pi sinc wt. Maybe I shouldn't write w because it's pretty similar to omega. So if you want, I can just write x. Yeah. Cool. So that's a Fourier transform pair that I looked at. So if we look at our function here, so our 2 intervals are -2 and 2. So you can write this as like the sum of -2 and 2. So we've got the sum of these 2 functions. We've got the rect function between -2 and 2, and the rect function between -1 and 1, where the value here is also 10, right? Because they between -1 and 1, they both add up to give you 20. Cool. So this would be rect of omega on 4. Yeah. And this would be rect of omega over 2. Because again, rect of omega is just the same thing, but between a half and a half and minus a half. So half and minus half. Yeah. Hopefully I haven't lost anyone so far, because I doubt many of you have heard of this function. So I can write f of omega as, so this is 10 rect omega on 4, and this is 10 rect omega on 2. So f of omega is 10 rect omega on 4 plus 10 rect omega on 2. And using the transform pair, I can get to the time domain function f of t. So I'll have a constant 10 out the front, and then I've got, so the width is, so remember we have 2x on the bottom where the width is x. So the width is 2 over pi sinc, so x is 2 here, 2t plus 10 times, and then I'd have x, which is 1 in this case, 1 over pi sinc xt, where x is 1 again, so sinc t. So I have 20 on pi sinc 2t plus 10 on pi sinc t, which if you have a look is pretty much the exact same thing that I graphed here. So there's 2 ways to go about it. honestly, like either way is fine. Like if you do the integration, it's not that bad because you're literally just integrating exponentials. The only thing that kind of involves you, the only thing that is kind of involved here is recognizing that you can pair these up and convert them into sinusoids, and then recognizing that you've got a sine t over t, so that's sinc. Question? So the rect function is just defined as, it's defined as a constant value of 1 between the interval of -0.5 and 0 everywhere else. Like it's a defined function. If you can look it up, similar to how sinc is defined as sine x over x. So going from there, because I've got two rectangles and they've got different widths, I have to write it as omega on 4 or omega on 2, right? Because if you divide a function, if you sub in f of x on a, that is the same as stretching the function in the x-axis. So that's why this is rect on, this is why this is rect of omega on 2 and this is rect of omega on 4, because I just have to stretch it. Does that make sense? Yeah, it's related to convolution. Like the function isn't derived from convolution, but you can, like it absolutely is used in like DSP contexts, this function, because like when you have like ideal filters, you ideally want them to filter out only some frequencies which are specified by like a width, and then you want them to attenuate everything to 0 everywhere else. So that's one context with which this function would be used in. And then obviously the context for this is, it's used very widely in signal processing, and so that's why it's kind of important to know Fourier transforms. Yeah. Okay. Cool. So moving onwards, what's the next question? Okay, so UT is a unit step function using Laplace. Okay, so it's just a Laplace transform question. Yeah, doing it in the Laplace domain. I think this is also helpful to show because honestly, solving second order RLC circuits in the Laplace domain is probably the easier way. In the exam, you can be asked to do both, which is annoying, but in like a real life context, I would almost always use the Laplace transform method, simply just because it's so formulaic. You can just kind of do it without thinking about it. Well, mostly. So, I think I'll add a new page. Cool. So let me draw the circuit. So I'm just going to draw it straight in the Laplace domain. So I've got a voltage source, and so it was 7 and times u of t, where u of t is the step function. So if you recall that just a u of t transforms into 1 on s in the Laplace domain. If that doesn't ring a bell, you should check the Laplace transform tables. They're your friend in this case. So 7 on s, and then you've got a 1 ohm resistor, and you've got an inductor here, which is, so the inductor transforms to, well, j omega L in the Fourier domain, so SL in the Laplace domain, so S times L. And you've got another resistor here, which is 1 ohm. And then you've got a capacitor, which was, so capacitors is 1 on SL, so 1 on SC. And then you've got a current source, which is also a step function, which was 3.5. So, yep, so 3.5, and then I've got 7 u of t. Yeah, and so the inductance is 1 Henry and the capacitance is 0.5 farads. So, so L is 1 and C is a half. So we end up with 2 on S. And that's our circuit. So, I mean, we are interested in V0T, where V0T is this, the voltage across the capacitor. Yeah, okay, so I would probably do mesh for this question simply because there's 3 loops and it's going to be quite easy. So let me redraw this ground node like this. Yep. So I'll notate my mesh currents. So I always do them clockwise, I think. So I1, I2, and I3. Yeah, too easy. So, so my mesh 1 equation will be -7 on S plus 1 ohm times I1 plus S times I1 minus I2 equals 0. So I've got 7 on S equals I1 plus S I1 minus I2. Yeah, so my mesh 2 equation is going to be so S times I2 minus I1 plus 1 ohm times I2 plus so 2 on S I2 minus I3. Yep. And then that whole thing is entirely equal to 0. My last mesh equation is going to be really easy because I can just there's a current source, right? So I can just make the rationale that I3 is equal to it's going the other way. So negative 3.5 divided by S. Yeah. Cool. So now I have 3 unknown variables and 3 unknown variables and 2 equations. So I can solve for I1, I2, and I3. I3 is already solved for us. And okay, so recall that the question wants V0 of t, which is in terms of the mesh currents, it's going to be, I can just use Ohm's law, right? V equals IR. So the current or the mesh current is I2 minus I3 times the impedance, which is 2 on S. So as long as I can get this, I'm fine. And I can inverse, the next step is to inverse Laplace that into the time domain because it wants V0 of t. Okay. Yeah, so now it's just kind of a matter of simultaneously solving this equation. So I'll get, so this is 1, this is 2, this is 3. So I want to solve for I2 since we already know I3. I can just kind of sub it in at the end. So I1 S plus 1 equals 7 over S plus S I2. Yep. So I1 is, and I'll do this. So S times I1 times S plus 1 equals 7 plus S squared I2. So I1 is equal to 7 plus S squared I2, and that's whole over S times S plus 1. Cool. And then I can sub that into equation 2. So S I2 minus I1, which is, yeah. Plus I2 plus 2 over S I2 minus I3, which is plus 3.5 on S equals 0. The backside equation subbed in, I've subbed in I3 and I1, so now I can just go ahead and solve for I2. And then after that, I can just find V0 of S, which is I2S minus I3S times the impedance 2S. Yeah. Okay, so how should I go about this? Okay, I'll times everything by S squared. So I've got S squared I2. Yeah, S squared I2 minus 7 plus S squared I2 over S plus 1 plus S times I2 plus 2I2 plus it's going to be 7 on S. Okay, so I can times everything by S again because I basically just want to get rid of the annoying denominators. So this is going to be 7. This is going to be 2S. This is going to be S squared. There's going to be an S out the top here. So 7S plus S cubed I2. And there's going to be an S cubed here. Okay. Okay, and then lastly, I'm just going to get rid of the bottom denominator. So S cubed S plus 1 I2 minus 7S plus S cubed I2 plus S squared S plus 1 I2 plus 2S S plus 1 I2 plus 7S plus 1 equals 0. Okay. Yes, it's a bit of a lengthy equation. I'm going to have to simplify it a little bit. And just checking my minus signs, can already see that. Yeah, there should be a negative here. So yeah, I think so. So that should be, yes, that's right. Okay. Yeah, I think I'm good to start collecting like terms now. So it's going to be I2, and I'm just going to go ahead and so there's an so it's going to be an S to the 4 term, and then an S cubed terms which cancel out. And then plus S cubed yep plus 3S squared plus plus 2S. Yeah. Yeah, that looks right to me. And then on the other side, I should have negative S plus 1 plus 7S. Yeah. Okay. Let me just check that. I haven't done anything dumb. So I times everything by S twice. So that's S cubed. Yeah, this is squared. Yeah, it looks all good to me. I have I2 equals S4 plus S cubed plus 3S squared plus 2S. Yeah. I think I've done something wrong. That's not what I remember it was. My one is, yeah, that's fine. I2 minus. Yeah, there shouldn't be a quadratic power. Sorry, a quartic power here. So I'm just trying to see where I went wrong. If anyone has a clue, let me know. Oh, is it that? Under the two. Oh, like here. S cubed. Yeah, because I times everything by S squared, I think. To get rid of, because there's S here and S here. So I want to, yeah.
Yes. The 7S.
Well, because there's an S on the bottom here. So timesing by S squared should get rid of that and then have another S. Yeah, I think that's fine, I think. Or maybe I times it by S just to make it so that there's no like nasty fractions. Yeah, there's an S in front of the brackets here. Yeah, so my mesh equations look right. Like they shouldn't be wrong. So I think it's just an algebra mistake. Squared by 2. Yeah, I mean, you should be able to do it with mesh though. I solved this like last night and it came out pretty fine with mesh. So I'm just trying to check where I went wrong. I mean, if I can't find it, I'll just stick to what I got because I simmed it as well just to make sure I had it right. So I know the answer. Yeah, because that should be negative. So there should be an S squared here, and there should be a 2S cubed here, is what I had before. So 7S. Yeah. It might be, did I do something wrong here maybe? So that's yeah, that's fine. So yes. Okay. I'll have to look at what I did because I literally cannot find where I went wrong. But I did this last night and simulated it just to make sure. So it should be I2 equals -7s plus 1 plus 7s squared. And then on the bottom should be 2s cubed plus 3s squared plus 2s is. Yeah. So now it's just a matter of inverse Laplace transforming back into the time domain. So oh well, we need V0. So V0 so V0 of S is so it's I2 minus I3 times 2 on S. Yeah. So I2 minus I3. So I'll just rewrite this. And I3, remember, is just -3.5 over S. So plus, I'll just write 7 on 2, or no, yeah, 3.5 on S, sure. And that whole thing is times by 2 on S, the impedance. So, so you should get 14 S plus 1 plus 14 S squared. And yeah, on the bottom here, we should have 2s cubed plus 3s squared plus 2s, and that's times by s. Actually, I'll probably factor out an s. I'll write it like this. Yeah, plus 3.5 on s squared. Yeah.
7.
Huh?
7 on s squared.
7 on s squared. Yeah, sorry, because 3.5 times 2. Yeah, 7. Cool. Yeah, hopefully that's fine. I hope that. Yeah, so let me just make common denominator. So 2s squared plus 3s plus 2. So I've got 14s minus 14 plus 14s squared plus, and if I make common denominator, it should give me 14s squared plus 21s plus 14. So the 14s will cancel, and I've got 14s squared. Yeah, 28, 14s squared. Yeah, I've got 28s squared. Plus, so 21 minus 14 is 7s. And since there's an s squared on the bottom, I can go ahead and kind of cancel it already. So 28s over s, 2s squared plus 3s plus 2. So this is the answer that you should get if you write out the mesh equations. Where you now have an expression for V0 of S, and transforming this into the time domain, you have to partial fraction it, because you need to separate the polynomials on the bottom. So let's just write this as A over S plus BS plus C over this quadratic, because I don't think this quadratic can be factorized unless I'm wrong. So let me check. 3 squared minus 4 times 2 times 2. Yeah, so the discriminant of this is -7. So you can't factorize this into like, let's say S plus alpha, S plus beta. So you just have to roll with this. Cool. Okay. So multiplying everything by the denominator, you should get A times 2s squared plus 3s plus 5 plus BS plus C, and then you've got 2s squared plus times S. So if we sub in S equals 0, we can straight away get A. So 7 equals A 0 plus 0 plus 5. So A is sorry, is that 5? No, sorry, that's 2. Yeah. 2. So A is 3.5, in other words. And then, so to get B and C, I can just kind of compare the coefficients. So compare S coefficients, or let's do S squared first. So on the left-hand side, we have 0 because there's no coefficients in S squared. And on the right-hand side, we have 2A because of this, the coefficient of S squared here is 2A. And then we also have B. So B is negative 2A, which is negative 7. And then last of all, we have to find C. So compare S coefficients. And then we've got yeah, so we've got 28 on the left-hand side, and then we've got 3A plus C. So C is 28 minus 3A, which if A is 3.5, that gives me 17.5. So those are my 3 constants now, which I can go ahead and plug in. So V0S is 3.5 divided by S, yep, plus, so BS plus C is negative 7S plus 17.5. And that whole thing is divided by 2S cubed plus 3S squared plus, sorry, this should be a quadratic. So 2S squared plus 3S plus 2. Okay, so doing the inverse Laplace transform, this is pretty easy because it's just a constant. The tricky thing is doing the Laplace transform of this. So the trick is whenever you can't factorize this quadratic, you have to complete the square, and essentially your answer is just going to be it's just going to be either a cosine or a mix of cosine and sine. So what I'm going to do, so to complete the square, you have to make sure that the coefficient in S squared is 1. So this is going to be 3.5 on S plus negative 7S plus 17.5. So I'll put a half at the front here because I factorized it. So okay. So now I can go ahead and complete the square. And if you remember, to complete the square, so S squared plus 1.5, I need to divide 1.5 by 2 and square it. So that gives me 3/4 squared, or 9 on 16. And then I have to immediately subtract 9 on 16 to keep the equation the same. So this is the same as S squared plus 1.5S plus 9 on 16 plus 1 minus 9 on 16, which I can go ahead and rewrite. So since this is a perfect square, I can rewrite that as S plus 1.5 divided by 2, which is 3/4 whole squared, plus 1 minus 9 on 16, which is 7. Yeah, 7 on 16. So plus 7 over 16. Cool. And then on the top, so we have times a half, and then on top we have minus 7S plus 17.5. Yeah. Okay. So yes. Okay, so in here we should have so we should split this up into cosines and sines. And the way I'm going to do that is I'm going to separate it into the I'm going to separate the S term and the constant term out, and then inverse Laplace transform that into cos and sine, which you'll see in a sec. So I've got minus 7, so minus 7S, and I need the same like shift here, because that means an exponential in a time domain, right? If I have f of like s plus a, like that's equivalent to, if you Laplace transform that, f of t, but just there's an exponential e to the e to the minus at. So So once again, I can write 7 times s plus 3/4 divided by s plus 3/4 whole squared plus 7 divided by 16. And now I just kind of have to, well, I have to keep the equation the same because I've just changed it, right? So I've got negative 7s minus 7 times 3/4. So I need to add that back. So that's 7 times 3/4. And then we have the 17.5 from before. S plus 3/4 whole squared plus 16. Okay, so we have that. And now I can write, so 3.5 on S plus a half. So this the left hand side, I can kind of leave it already because it's already ready to be transformed into the time domain. And here on the right, I'm just going to add those two up. So 7 times 3/4 plus 17.5 is about 22.75. And then I've got the same thing on the bottom. Plus 7 over 16. So I guess it might be worthwhile for me to actually write out what the Fourier transforms are. So if you have S over S squared plus omega squared, that's cos omega t. And then if you have omega over S squared plus omega squared, that is sine omega t. So if you want to add the exponential, if you want to have e to the minus alpha t, then this gets changed to s plus alpha, and you just replace s with s plus alpha. So s plus alpha squared plus omega squared. And then likewise, if you want to have e to the minus at here, and that's just that is also a property that you can get to, but this pair is also in the usual Laplace transform table. So s plus alpha squared plus omega squared. Cool. So my omega here is the square root of that. So it's square root of 7 over 4. So I need that on the top. So I need that on the top, which plus a half. Oh, okay, so I've got I mean, I'll just write dot 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 because I'm not going to bother writing it again. So then you've got root 7 on 4 over s plus 3/4 squared plus 7 on 16. And so I'm going to times it by 4 over root 7, and then we still have 22.75. So now I'm all good to transform this back into the time domain. So V0 of t is, so 3.5 on S just transforms to 3.5 U of t. And the top here I have this, which is just negative 7 e to the minus 0.75 t, right? 3/4 is 0.75. And then I've got cos of root 7 on 4 t, because that's my omega. And there's a half at the front, so 7 on 2. And then I've got plus this thing divided by 2. So 2 times 22.75. So 45.5 divided by root 7. Oh, hang on, sorry. I've times it by 2. I should divide it by 2. So oops. Yeah. So this should, my calculator gives me 91 over 2. And then this goes e to the minus 3/4 t. So 0.75 t sine root 7 on 4 t. And that entire thing is u of t tacked onto it. Yeah, so it's very involved. It's a very involved question. And this should sorry, there should be a root 7. Yeah. Yeah, it's a pretty involved question, and I'm not sure what I did wrong there, but it should, yeah, you shouldn't have a quadratic at the front. I guess I just made an algebra mistake, but my mesh equations are fine. I do have the solution with the actual answer on it, so I will upload that. But yeah, that's the answer to that question. How are we going for time? So we've got about 20 minutes left. What's next? Okay. Okay, so we've got another Laplace question. So consider the transfer function h of s. Is that, and then sketch the poles and zeros, and then sketch the magnitude response. Okay. Okay. So I've got h of s equals 5s plus 13 s cubed plus 4s squared plus 13s. Okay. And oh no, hang on, we've copied down the wrong thing. Sorry. Oops. So it's s squared plus 1 divided by s cubed plus 4s squared plus 13s. Oh, sorry, plus 13s. Cool. Yeah, so to find the poles and zeros of this, so remember the poles are your solution to the denominator and your zeros are your solution to the numerator. So the zeros of this are, well, you just solve the equation s squared plus 1 is 0. So obviously your two answers are going to be plus or minus j. So you have two zeros at j and minus j. And then for your poles, so you can write this as s times s squared plus 4s plus 13. So immediately you can see there's a pole at 0 because all you're solving is this equation equals 0. So there's a pole at 0 and there's another pole at s equals, and I'm just going to use a quadratic formula. So minus 4 plus or minus 4 squared minus 4 times 13. And then that entire thing divided by 2. So putting that into my calculator, I get so s equals 0, s equals minus 2 plus or minus 3j. Yeah, so those are my two roots. So I have 3 poles, and I think it said sketch the poles and zeros. So I'm gonna go ahead and do that. So this is my real axis, and this is my j omega axis. So remember, we use x's for poles and zeros for zeros. So the poles, there's one at 0, and there's one at minus 2 plus, minus 2 plus or minus 3j. So over here and over here. And then I've got 2 zeros at plus or minus j. So go ahead and do that. So this is j, this is negative j, and I've got 2 zeros there. Cool, and that's how you do it. So then it says, hence or otherwise sketch the magnitude response h of j omega as a function of omega, showing the values of at least 2 points on the response. So the way to kind of do this is, just sub in s equals j omega, and then, well, find the magnitude of that. So I'll just find h of j omega first. So that's s squared plus 1 was, if you sub in s equals j omega, that gives you minus omega squared plus 1. And then on the bottom we had, right, s cubed, which is minus j omega cubed if you sub in j omega, and then minus 4 omega squared plus 13j omega. So all I've done is I've just subbed in s equals j omega, and I get this. So the magnitude response of that is, so the magnitude of 1 minus omega squared, and then I've got the magnitude of this thing, which is the square root of 4 omega squared whole squared plus 13 omega plus omega cubed whole squared. Because if you want to find the magnitude of a complex number, you just have to, it's just the square root of the real part plus the complex part squared. So alpha squared plus beta squared, and the square root of that. Okay, yeah. And then and then I mean you can just sub in like omega equals 3 and whatnot. Because it said where was it? It said sketch the magnitude response showing the values of at least 2 points in the response. Okay. So well, we can immediately see that is the function is going to be 0 when you sub in omega equals 1. So if I start out the plot, so I have omega on the x-axis and the magnitude on the y-axis. First of all, if you sub in omega equals 0, you can immediately see that the denominator blows up, right? Because the denominator equals 0, so you just get infinity. So it starts at infinity, and then you know that at omega equals 1, it's going to equal 0 because of this. So it looks like this. So infinity here, and then you can pretty much sub in like any other value and notate that. The way that the solution to this did it is it just recall that your poles will influence the maxima of the system, and your zeros will influence the the minima of the system. So I think we said that, yeah, so there's a pole at this, which is omega equals 3 because of this 3 here. So there'll be a maximum somewhere about 3. So if you sub in h of, and then as omega goes to infinity, right, you have something of degree 2 here. So on the top, right? So this is degree 2. And then on the bottom, so you essentially have a quartic because of this omega squared, and that's rooted. So, oh no, that's still fine. Oh yeah, okay. So you've got a cubic here, and that's squared. So that's to the power of 6, and that whole thing is square rooted. So you effectively have some function that looks like a cubic. So degree equals 3. And because the degree of the denominator is greater than the degree of the numerator, so that means that as we go to infinity, then the transfer function is just going to go to 0. So it looks something like this. Well, you know that, okay, so you know that the transfer function has to approach 0 as you go on. And you know that it can't be negative because it's a transfer function. So the transfer function looks something like this. Yeah, like that. So you've got a pole at 0 and a pole at -2 plus 3j. So that is kind of evident here. So because at 0 you've got the function blowing up to infinity, and you should have a maxima somewhere around 3. Cool. So and then for the actual value, you can just go ahead and sub in omega equals 3, which gives me 4 times 3 squared plus gives me like 0.106. Yeah, and so that's how I would do that question. Cool. So I think we have time for maybe one more. I'll do SE power? Yeah, sure, I can do that. Oh yeah, okay. So there's this. Yeah, I'll do question 1. So okay, yeah. So this is 2018 question 1. So it wants you to find the average power and reactive power delivered by the source. And then the power factor, the phase current I, and the power triangle for the source. Okay, right. So we've got two loads that are connected in parallel here. So we've got A and B. And if you think about the complex power, so SA and then SB, so if you think about the complex power, what happens is the average powers add up and the complex powers also add up. So essentially you end up with S total equals SA plus SB. So I'll add a new page. Cool. So you want, okay, I think what I'll do first is I'll sketch the two power triangles because it's giving us some information about the power triangles. Yeah, so if we want the total power delivered by the source, we're going to have to find S total, right? Because this is the source and it's delivering power to both of these loads. So if we just add them up, we should be able to get the total complex power. So I'll redraw what I have here. So it's 1414 with a phase of 30, and that is a source. And then we've got two loads. So load A, it said was 10 kilovolt amps, and the power factor is 0.5 leading, which means a negative power angle. So, so 10 kilovolt amps, remember that volt amps is a unit for apparent power. So this is 10 kVA, and the power factor is, so if I do cos inverse 0.5, that gives me 60 degrees. Yeah, that gives me 60 degrees, and that's negative because we have a leading power factor. And then I can just use trigonometry to really find the rest of the, so I want the P and I want the Q. So Q is, so sine 60 is Q divided by 10 kilovolts. So Q is 10,000 sine 60, which is 8660 volt amps reactive. And then P is similar thing. It's 10,000 cos 60. So 10,000 cos 60, which should just be a half. Yeah. So 5,000, and that's in watts. Then the next power triangle, I think, is so 5 kilowatts lagging. So that means positive power angle. So we've got this. And if I do cos inverse, so 5 kilowatts, and the power factor is 0.7 lagging. So if I do cos inverse 0.7, I get about 45.6 degrees and 5 kilowatts. Cool. And then again, I can just use trig to find this Q, which is just use tangent. So 5,000 tan 45.6, right? Because tan Q on P is tan 45 is Q on P. Okay, so that gives me 5,000 tan 45.6, which is about 5106 volt amps reactive. So the total power triangle I can get if I just add these two triangles together. So if I add, so S total equals, so I had 5,000 watts, and then I have 5,000 more watts on the other triangle, and then I have negative 8660 volt amps reactive. plus 5,106. So that gives me 10,000 plus J, and this gives me, oh, it's negative. So negative 3,554. Yeah, and that's in volts. Oh, sorry, that's apparent power. Yeah, so that's the value for the complex power. Okay. Yeah, so from here I can just get the average power, which is 10,000, and the reactive power, which is about 3,550. That's volt times reactive, and that's watts. Yeah. So the second question says the power factor for the total impedance seen by the source. The power factor by the total impedance seen by the source. Well, yeah. So if you look at this triangle again, well, I'll redraw it. It looks like this. So got 10,000 here, and then we've got 3,554. And all I have to do is calculate the theta, or the angle, which I can get using tan. Which is about 19 degrees. And if I do cos of that, I get 0.942. And that's leading, because the power angle is negative, so leading power factor. You must remember to specify whether it's leading or lagging, otherwise they can't tell what you mean. So you will probably lose marks. Okay. Next question was the phase current I. Okay, so I is this thing. Yeah, so I is this current. And to find I, am probably I'm probably going to look at the complex power. Yeah, because the complex power is, so the complex power is half times V times I conjugate, and this is I, and this is the voltage, which we know is 1414. And these aren't in RMS. The question didn't specify what it didn't say that it was in RMS. So that's why I have this factor of a half out the front. So I can get I conjugate is S total times 2 divided by the voltage. So 2 times S total, which is 10,000 plus, sorry, minus J 3,554. That whole thing is divided by the voltage 1414 with a phase of 30. Which when I put into my calculator gives me 1414 phase of 30. So that gives me 15.01 with a phase of negative 49.6 degrees. And that's I conjugate. So to get I, you can just flip the angle to be positive, and that should be the answer in amps. So then the last question says, sketch a power triangle for the source, clearly labeling the real, reactive, and apparent power in any relevant angles. Okay, so we already kind of did that, but I guess I'll just redraw it. So we've got this because the angle is leading. And the angle was, I think, 19 degrees. And the power was 10,000 watts. The reactive power was 3,554, I think it was, volt amps reactive. And then the Complex power you can just get by just doing the Pythagoras sum of these. So 10,000 squared plus 3,554 squared. So it gives you about that many volt amps. Yeah, and that's about it. Should I do any more, or is that enough? Yeah, okay. Thanks to everyone who joined this session. I will provide the answer to all of these questions and ones that I didn't cover, because I think I didn't cover a couple of questions. So I'll send that to ELSOC and then they'll probably link you guys up. Yeah, does anyone have any last questions before we end the session? Yep. What do you mean by which finals? Oh, like the ones on Moodle? Yeah, it depends on apps. I don't think he likes releasing solutions, especially for the more recent ones. I don't think there are, which is why some of the questions I've gone through are like 2019 and 2021, which don't have solutions. So yeah, I don't think so, realistically. But I mean, I guess you can just kind of compare with your mates. So yeah. Okay, if no one has any questions, then yeah, thank you all for coming, and yeah, good luck with your finals.